Welcome to Monochemistry. Today we're going to look at the heat of a reaction. And the first thing we're going to look at today before we get into the actual heat of reactions is what's known as a potential energy diagram. There are two diagrams. This one that we're looking at here is for an exothermic reaction. And I'll explain that in a second. But you can go ahead and copy this diagram down. Make sure you have all the different parts that are labeled there, A, B, C, D, and we're going to fill in what those are, okay? So this is for an I got my red and green going on here. It must be Christmas time. Exothermic reaction, and the next graph that I'm going to show you is for an endothermic reaction. We'll get to that in a minute. Okay? So for this graph, we've got potential energy on the y-axis and reaction coordinate, or you can cross out coordinate and put progress. That's fine too. Reaction progress would work there too. Okay, so here, not A, but right here, these things right here are the reactants. Okay, the reactants are right here. The products are right here, not D, okay, but in general, these are the products. Okay, so what we have here is we have, basically you're following the potential energy throughout the reaction. Okay, so what happens to the amount of energy flowing throughout the reaction? So what you notice right away is that the reactants have more energy than the products. And if ever you see a graph where the reactants have more energy than the products, right away you're going to say it's exothermic, because the reactants have more energy than the products. What that means, ladies and gentlemen, what that means is these substances are going to release energy, okay, to form these substances. Okay, so in other words, you have more energy on the left-hand side of your equation than you do on the right-hand side in terms of inside the substances. This is going to release energy to the surroundings. Therefore, it is exothermic. Okay, now, what I'm going to show you here is a couple of different things. First of all, A is the amount of energy that the reactants have. D is the amount of energy that the products have. C is not really important here, but B is the amount of energy that is required to start the reaction. It's known as the energy of activation. Okay, energy of activation, sometimes abbreviated E. Oops, wrong one. Sorry, guys. Sometimes abbreviated EA. Okay, so energy of activation is right there. Now, what is the delta H of this reaction? In other words, what is the energy change in this reaction? Well, in this reaction, because we're looking at the amount of energy that the reactants have versus the amount of energy that the products have, the delta H of this particular reaction is going to be equal to, I'll show you in a sec, question mark. It's going to be equal to, the delta H of the reaction in this case is going to be equal to D minus A. Now, why is it equal to D minus A? Because remember, change in is always final minus initial. So D minus A. And guess what? That is going to give us a negative value. Now on the graph, okay, remember we're not going to use C, but on the graph I want you to draw in a line from here to here. Okay, we're going to call that E. The distance between here and here is E. Sorry, my fat fingers aren't doing so well with that. Okay, so we got E. E is equal to the delta H of this reaction. Okay, the difference between A and D, or in this case D minus A. And because we're going down in energy, our reaction will end up with a negative delta H. Okay, make sense? All right, let's move on. Make sure you copy this down. It's a good note. Okay, now we have the potential energy graph for an endothermic reaction. Uh-oh. There we go. Must be too close to the top, guys. Endothermic. Sorry about the writing there. Not very good. Anyway, so as you can see, we have labeled here. These are the reactants. These are the products. What do you notice right away? Well, the products have more energy than the reactants, Mr. Monahan, so therefore this must be an endothermic reaction. Okay, so this is the amount of energy that the reactants have, and this is the amount of energy that the products have. What's this? Yeah, that's right. It's delta H. This is the delta H because it's the difference between 4 and 1. Now, watch. So delta H of this particular thing is going to equal B, no, not B, sorry, undo, 4 minus 1, and not really 4 minus 1 equal 3, but this 4 minus this 1, which is going to give us, believe it or not, that does actually work out, we're going to get a positive 3. Okay, so final minus initial to get the delta H of the reaction. Okay, and of course that means that it is, because we get a positive value, that means it's endothermic. 2, okay, so there is our delta H. Now 2 is the energy of activation. Okay, so it requires that much energy to get the reaction started. That's what that is. All right, so make sure you copy this one down too. Okay, so that's the two different types of potential energy graphs. And remember, it doesn't have to be reaction coordinate. It can be reaction progress instead. It's fine. That might be what you see in the textbook. I can't remember exactly. But let's just go on from here. So what are the differences between heat, or Q, and delta H? What are the differences between those? So if I wanted to look at the differences here, just mathematically, so we'd have Q is equal to N, which is the number of moles, times delta H. Okay, so if this is Q of the reaction, let's say, that would be, the Q of the reaction would be equal to N delta H of the reaction. Now the delta H of a reaction, mathematically, if you think of it this way, would be just a rearrangement of that, and it would be equal to the amount of heat divided by the number of moles. Okay? But delta H in itself, right, remember, is the change in energy of a reaction. Okay? And the change in energy of a reaction is per mole. So it's dependent on the fact that there's 1 mole. Q, on the other hand, allows us to calculate the heat given off or taken in by a reaction based on the number of moles. Okay, so they're very much related, but delta H itself is a standardized thing, and it's per mole of a substance. Whereas Q allows us to figure out how much energy is released or absorbed, depending on if it's exo or endothermic, by taking into account the number or the amount of the substance. Okay, so they're very much related. Obviously, delta H is a change in energy, and Q is the amount of heat. Okay, it's not a change in, it's based on the change in energy, but it's the amount of heat released or absorbed. Okay, and that's the difference between the two. And that, in a nutshell, is how definition of heat of reaction. Heat of reaction is the amount of energy given off or taken in during a chemical reaction. That's the definition I want you to write down for heat of reaction. And that, in a nutshell, is how you read potential energy graphs and the differences between heat and enthalpy.